Hello, everyone. Can you hear me?
Yeah.
Yes.
Oh, perfect.
Yes.
All right. So many of you know me. I know many of you. I'm Nicolae Țarfulea, professor of mathematics in the Mathematics and Statistics department. And my colleague and good friend, Dr. Elias, asked me to substitute for her today. And that's pretty much what it is. And I'm going to turn off the camera. I don't want my handsomeness to be a distraction to you. We'll talk about a very important subject today, namely about determinants. Okay, so you can ask me questions anytime you want. You can stop me and ask questions anytime you want. I'm gonna send a video lecture to Norma, and she'll post it on Brightspace. Okay, so let's begin talking about determinants. I'm going to share with you my screen, and let's start by emphasizing the importance of this, like I said, very important topic in not only in linear algebra, in many other fields. And I'm gonna say, you know, this is chapter 3 in your textbook. It's just an introduction to determinants. So this is, I'm gonna talk about section 3.1 first. So this section 3.1 is about an introduction to determinants. Okay, you have probably heard about determinants even in this class. Definitely you did. And you probably know the definition of at least 2x2 determinants. Determinants are really important objects, mathematical objects. So for example, the area of a parallelogram can be computed by using determinants. So applications of such determinants. Applications. I'm going to mention just a few. Actually, somebody wrote 2 volumes in long ago. Thomas Muir wrote 2 volumes of such applications, and it was long ago. There are many more, you know, now. The area. So this is one of the, you know, one application, area of a parallelogram. In other words, if you have 2 vectors, let's say A and B, something like this. So this is A, let's say vector A, and this is vector B. Then the area of the parallelogram constructed on these 2 vectors, this area, is given by the determinant, the absolute value actually. You don't want an area with sign. The determinant of this matrix A, so it's a notation, where the determinant of A is just the determinant of the column which has as entries the column vectors A and B. So here you have A sub 1, A2, B1, B2, where I'm really sorry about, you know, my handwriting. The tablet is not cooperating too much now. Where these 2 vectors A are and B are, you know, column vectors, like I said, having components A1 and A2, A, and B has components B1 and B2. So this gives, you know, the area of a parallelogram. Of course, you can, another application is the volume of a parallelepiped. So the volume, okay, just a second. Right, the volume of a parallelepiped constructed on three vectors, A, B, and C, three-dimensional vectors. So something like this. So you have, you know, let's say this is vector A, B, and C. And you construct a parallelepiped by using these three vectors, obviously something like this, more or less. Okay, then the volume of this parallelepiped is given by the absolute value of this determinant of a matrix, of this, the matrix A, where the matrix A consists of the entries of these three vectors A, B, and C. So A, okay, so let me see what people, do they have questions? Well, yeah, I mean, I'm going to define the determinant, don't worry. So just, you know, stick with me. All right. So A is this matrix consisting of the entries of the vectors A, B, and C. So this is A1, A2, A3. That's the first column. B1, B2, B3, C1, C2, C3. We'll learn how to compute such a determinant, but the volume is given by the absolute value, the magnitude of the volume is given by the absolute value of the determinant of this matrix. So this is another important application. Now, you probably, since we are here, you know that when you use the change of variable formula in Calc 3 for multiple integrals, you also have the determinant of the Jacobian transformation. It's something like this. So if you have, let me just come back here. So if you have, you know, this, so this is another example, 3. Let's say you have you want to compute the integral over a, let's say, domain in the plane, and you want to change the variables. Let's say you want to pass to, let's say, polar coordinates, for example. So let's say the polar coordinates look nicer. I mean, the region where these polar coordinates are may look nicer than your original domain. So let's say, you know, these are the parameters u and v, and let's say you want the integral over this region, which is not very regular. I mean, not very nicely looking. It's not a rectangle or anything. So let's say this is S, this region. And let's assume that you want the integral over S of a function, f of x and y. So here is, you know, the x-axis, the y-axis, and you have a transformation, that a diffeomorphism, which brings this rectangle into that region. So let's call it phi, okay, phi. Well, you remember from Calc 3 that the integral, the double integral of this function f, whatever function f you may consider, call it like a density function if you want. and you compute here the mass of that lamina. If you want to have a physical interpretation, well, you remember that this is the double integral over R. This is what you said in Calc 3 of f of x of u and v. I mean, of course, x and y depend on u and v in this region. Y of u and v. And here is the determinant of the Jacobian matrix of phi at this x of u and v, y of u and v, and then you say here du dv. And of course, you have something similar in 3 dimensions. So again, we have a determinant here. This is a determinant. So determinants enter pretty much everywhere in many areas of mathematics, engineering, and sciences, and not only, right? So this is a determinant. Okay, let me remind you what you said about determinants in the past, because I'm pretty sure you said something. I saw in the textbook that you had something in chapter 2. You have a computation of the inverse matrix. You had a 2 by 2 matrix, and you had a computation of, a formula for the inverse matrix, and that involved a determinant. So let me remind you the definition of the 2 by 2 determinant. So the 2 by 2 determinant. Here is the definition. So you have, the determinant of this 2 by 2. Just a second. Let's say you have these entries A, B, C, D. Do you remember what this is?
Yes,
Jacobian, not Jacobian, Jacobian from Jacobi. Maybe it's my pronunciation. Okay, Jacobian. So this is the Jacobian. Jacobian, in fact, it's the determinant of the Jacobian matrix, which plays the role of the derivative for multivariable functions. Okay, you should know this from Calc 3. What's the determinant? What's the 2 by 2 determinant here then? Do you remember this?
A times B minus B times C.
Okay, so A times D, that's correct, minus B times C, or C times B, same thing. So it's the product of the elements on the main diagonal minus the product of the elements or entries of the second diagonal, of the secondary diagonal. So for example, if you have something like this, let's say -1, 3, 4, 7. What's this? Is -1 times 7 minus 4 times 3. So I have -19. It's a number, right? Okay, how do we extend the definition from 2 by 2 determinants to 3 by 3 determinants, 4 by 4 determinants, n by n determinants in general? So let's say, you have this n by n matrix. So let's consider this matrix A, an n by n matrix. It has n squared entries, obviously. So you have A11, A12, A1n, n entries on each row and n entries on each column. And here, let's say you have, let me scroll down a bit. So this is the, let's say sub I1, I mean the ith row, maybe I should, do a column as well. I mean the generic column, jth column. Let me just modify this a bit. So I can say here, okay, so you have here A1J and so on. Here you have A1N, and here you have AIJ, right, at the intersection. Okay, and AIN, AN1, this is the last row, N2, NJ, ANN. This is an N by N matrix. Okay, now let me introduce a few notations. So the notation I'm going to introduce are very useful and will help us to define the determinant in general. So the first notation that I'm going to introduce is this one, the so-called AIJ. This is another, so this is an N minus 1 by, so this is an N minus 1 by N minus 1 matrix associated to our matrix A by crossing out row I and column G. So which is obtained by crossing out row I and column G. So in other words, I get rid of this row, so this is out, and this column in general. In this way, I obtain an N by 1 by N by 1 matrix, which is associated to our matrix A. It keeps all the other entries in it. Another notation, which is also very useful, is this one, the so-called CIJ, which is also an N minus 1 by N minus 1 matrix. And its formula is this. It's just, well, I'm going to tell you what the determinant is immediately. It's just maybe I should, okay, I'm gonna write it here, and then I'm gonna define the determinant. So I'm gonna go back to this thing. So this is just -1 to the I plus j. That's something that we can understand now. But then you have the determinant of this matrix, which is still undefined, right? So let me define the determinant. So let me give you, so these are the notations that I'm going to use. Now, the definition of the determinant. Okay, well, it's kind of a recursive definition. So in other words, it says this: if you know how to compute determinants of order n minus 1, then you have a formula for computing determinant of order n. So for example, now because we know how to compute determinant of order 2, we'll know how to compute determinant of order 3, then determinant of order 4, and so on, right? So here is the formula. So the determinant of our matrix A, by using the notation above, is just the first entry, A11, times the determinant of A. I'm going to give, concrete examples, numerical example to understand this thing, minus the second element on the first row times the determinant of A, 1, 2, and so on, right? Plus -1, the signs are alternating, as you can see. Okay, A1n times the determinant of A1n. Okay, if you want, you can write this in a more compact way. You can say this is the sum from j equals 1 to the n of -1 to the 1 plus j of A1j times the determinant of A1j. Okay, all right. Now let's see an example, because otherwise these things can become really unappealing. So here is an example. Let's compute this determinant, a 3 by 3 determinant. So I can say here this is 1, -2, and 3, 4, 0, 2, -7, 5, and say -1. This is the determinant of a 3 by 3 matrix, right? It's a three-dimensional determinant. Okay, was this according to the above formula? So this is, A11. A11 is this. This is A11 in our case. So this is 1 multiplied by the determinant obtained by crossing out the first row and the first column. So here you have 0, 2. This is what's left. 5, -1. Minus this element here. So this one is A1, 2. So minus 2. And the determinant obtained from, corresponding to crossing out the first row and the second column. Maybe let me see if I can erase, a few things. So I can erase this. Now this one. Okay, perfect. So now I cross out this and this, right? And here I have 4, 2, -7, -1. It's a two-dimensional determinant that I know how to compute. And finally, plus 3, so this element here, which is A13, multiplied by the determinant of the matrix obtained by crossing out the first row and the last column. I'm going to erase this. Erase a bit too much. So let me put it back. Here it was -2, right? Okay. And now I cross out this, the first row and the last column. And here you have 4, 0, -7, 5. Okay, now I know how to compute this, right? So this equals 1. You just, I'm going to keep it here, although it doesn't do anything. What's the first determinant? What's the determinant of this matrix A11? So this is A11. This one here, I mean, is the determinant of that matrix, actually. The determinant of that. This is the determinant of A12. And the last one here is the determinant of A13. Okay, so what's the first determinant? -10, right? So it's 0 times -1 minus 5 times 2. So that means -10. And then you have plus 2, -1 times -2 is plus 2, times what? It's 4 times -1 minus 2. So here in this parenthesis is 4 times -1 minus -7 times 2. Well, so you have -4 plus 14. So it's 10, right? And finally, plus 3. The last determinant is 4 times 5, which is 20, minus 7 times 0. Well, 20 minus 0, so this is 20. All right, and now we can, we have our answer. So the answer is what? Is 70, a number. That's our determinant. Do you understand how we computed this?
Yes.
You can say it. Okay. In fact, you can, the determinant of an n by n matrix A can be computed by a cofactor expansion across any row or down any column, not only the first row or the first column. So you can compute the same number. So let me show you the same determinant in this way. So this is we completed this determinant by expansion across the first row. You can also compute the same determinant by expansion down the first column. So the same determinant. Let's look at this one. We should have obtained the same number. So we have 1, -2, 3, 4, 0, 2, -7, 5, -1. I can write it like this. I can say this is 1 times the determinant, this determinant, you cross out the first row and the first column. Is like, the one which we had before. So here is 0, 2, 5, -1. But then you say -4, this 4, multiplied by this determinant. You cross out the first row and the first column and the second row, or the second row and the first column. And here you have -2, 3, 5, -1. And then finally, plus, we have -7 here, multiplied by this determinant. So you have to eliminate the row and the column whose intersection is -7. So I'm gonna try to erase a few things. Uh-oh, too many. Okay. Have to put it back. So here was 1. So for this, I cross out the third row and the first column, and what I have here is -2, 3, 0, and 2. Okay, so let's see what we have in this case. We should obtain the same thing. So this equals, all right, so this is 1 times negative 10, right? So 1 times negative 10, that's the first determinant. So here, what I have here is just the determinant of A11. Again, this one is the determinant of A, okay, 21. And this one here is the determinant of A 31. All right, minus 4. What's the determinant? This determinant is 2 minus 15. 2 minus 15 is negative 13. Okay, and here I have minus 7 multiplied by negative 4. All right, so let's see what we get. So this is negative 10 plus 52 plus 28, right? Well, if you add up these numbers, you end up with 70 again, which is exactly like here. So what we used here, we expanded along the first column. You can do the same thing along, I mean, across any row or column. You obtain exactly the same thing. So I can write this as a little theorem if you want. I can say here, where is that thing? Okay, yeah, the cursor. There is a little theorem which says that the determinant of a matrix, an n by n matrix, A, can be completed by a cofactor expansion across any row or down any column. So in other words, you can write it like this. So you can write it as A I1 C I1 plus A I2 C I2 plus A IN C. Remember what these, cofactors, IJ cofactors were. IN, but this is also equal to A1J C1J plus A2J times C2J and so on. Okay, so I'm gonna do some examples. So let's see what I mean by this. Just a second. C and J. But this is very important. So it doesn't matter what row or column you choose. The cofactor expansion is the same. So let's consider another matrix. I'm going to consider a larger one. Let's say I'm going to make up this one. So I can say here negative 1, 2, 3, negative 4. Here I can say negative 2, 0, 1, 0, and let's say 3. I'm choosing nice entries because I don't want to compute complicated let's say numbers. I can say here, I don't know, 0, negative 3, 5, 1, 0, 4, 7. And let's say we want the determinant of this matrix A. Okay, so we want the determinant of this matrix A. So I want this. Choose the row or the column along which we expand this determinant. So what would be a very advantageous row? So let's say we want to compute this determinant by cofactor expansion across a row. What would be the best row to choose? What do you think? The one which has the most zeros, right? Because you compute the least determinants. I'm going to use this row. Okay, so what do I have here? So the first element is -2, right? Then the cofactor. You know that the cofactor, the corresponding, so here you have, negative, maybe I should write, in these terms. Say C, here is the second row, first column, plus 0 times C of Q2, right? But this doesn't matter anyway. Plus 1 times C Q3, plus 0 again times C, okay, Q4. That's the expansion along this row, across this row. Okay, so what do we have then? So this is -2. What's the cofactor? Remember the definition, the ij cofactor. Cij was defined as -1 to the I plus j times a ij, right? Okay, in our case, well, we have to get rid of the, cross out the first column and the second row. So what you have here is 2, 3, -4, okay, and then you have 0, -3, 5, and then you have 0, 4, 7. I forgot something, right? What did I forget? -1 to the 1 plus 2. That's not negligible. So I should have written it here. I'm going to insert it in that place. All right. So this is -2, in fact, multiplied by -1 to the I plus j. In our case, I is the second row, right? It's 2 plus 1. So that means 2 plus 1 here. 3. Okay, now the other one, I don't really care. I mean, this one is 0, so I'm not going to write it. The other one here is also 0. And the one which is left is plus 1. Again, you see the signs alternate. Okay, so you have here I started with okay, so here you have, the sign alternates because you have -1 to I plus j. So here you have, in this case, have 1 multiplied by -1 to 2 plus 3, which is -1, multiplied by this matrix, which I obtained by crossing out the second row and the third column. So what's left is -1, 2, -4, 3, 0, 5. Okay, what's 1, 0, and 7. Okay, now look what we got. So we got 2 times this determinant which is not very hard to compute. And you should tell me why. You should take advantage of the 0 entries, right? We should take advantage of that. Well, 4, 7. And here is negative. Negative 1, 2, negative 4, 3, 0, 5, 1, 0, 7. Okay, so this equals. Okay, so how do we compute these determinants? So let's compute the first one. So I'm going to compute this one. Okay, so which is what? How do I compute it? I expand along, down the first column. This is what I'm going to do. So this is what? It's 2 times negative 1. I'm going to write, the cofactor 1, 1 to the 1 plus 1. Okay, multiplied by, you cross out these 2, and you multiply by negative 3, 5, 4, 7. And then you have only zeros. I mean, all the other entries on this first column are zeros. So you can say here, if you want, plus 0 times this cofactor, 2, 1, but doesn't matter, plus 0 times C, 3, 1. These are zeros. And so the first determinant is just 2 times, okay, here I have 21, negative 21, minus 20. So, okay, minus 41. So I got negative 82. All right, so I have 2 times negative 82. And now the last, how should I compute the second determinant? This determinant. What row or column should I use? I mean, what would be, the most advantageous? Usually it's helpful for computation, for computing the determinant of a matrix if it contains zeros, right? I mean, if the row or column you use contains zeros. So that leaves us with this. So let's see how we expand this thing. So here you have 3, 0, 5, 1, 0, 7. Right? So I'm going to use this column, right? So this is what? Well, it's 2 times this cofactor, C, first row, second column, okay, plus 0 times C, okay, second row, second column, plus 0 again, times C, third row, second column. Of course, these two are 0 no matter what those cofactors are. And all I have to do is to compute this one, which is what? C12 is negative 1, the 1 plus 2. And then A22, well, actually, A12, sorry. A12 can be obtained by crossing out the first row and the second column. So what I have here is 3, 5, 1, 7. Okay, so we are almost done. So this is negative 2 because negative 1 to the, to the 3 is negative 1. And then I have 3 times 7, 21, minus 5, 16. Okay, so look what we have here. We come back, we have minus 32. It's a number, right? So it's minus 164 plus 32 turns out to be negative 132. Is this understood how you compute determinants? I mean, basically, this is the definition of the determinant, if you want. Keep in mind that, you know, the signs are alternating. Either you use the cofactor notation or you use the AIJ notation, I mean, capital AIJ notation, but keep in mind that the signs are alternating, okay? Again, it's helpful for computing the determinant of a matrix that contains many zeros, right? So like we did here, we use that fact. As a consequence, if the matrix A is a triangular matrix, so let's talk about triangular matrices. So let's say a remark. If A is triangular, meaning something like, let's say it's a upper triangular. So let's say we have an upper triangular matrix, meaning, you know, this element here is A11, then A12, A1n, and then you have zeros here. And then you have A22, A23, A2n, but then, you know, zeros above the main diagonal everywhere. And here is ANN. By using the definition of the determinant, the determinant of A in this case is just the product of the elements on the main diagonal. Same thing for lower triangular matrices. So this is for upper triangular matrices. Same thing for lower triangular matrices. You obtain exactly the same thing. So for example, so let's say an example. Let's say you consider this matrix upper triangular. 1, negative 2, 3, 0, 4, 7, 0, 0, 11. What do you think is the determinant of this one? What's the determinant of this matrix A? Anybody home?
Um, 1 times 4 times 11.
Very good. 1 times 4 times 11. And this is 44. How do you prove this? I mean, because, you know, you can prove this in general. In fact, you can say, so I'm going to prove, you know, this formula. So let's try to prove this formula. So here is the proof of that formula. The determinant of that matrix A, which is A11, keep in mind that these are all zeros. The entries below A11 are all zeros. And then this is A1n. Then you have, okay, let me write one more here, A22, all zeros below that, ANN. Well, according to the definition, this is A11. So I'm going to expand this down the first column, multiply by C11, and then all the others are zeros, right? 0 times C21 plus 0 times, these are the cofactors in this case, Cn1. These are all zeros. So meaning that what I have here is just A11 times negative 1 to the power 1 plus 1. I'm writing the definition of this 1, 1 cofactor. And what's left here, this is the cofactor. I mean, you cross out the first row and the first column is just A22, zeros below, I mean, underneath this entry, A23, A2N, then here you have A33, zeros again, ANN. And if you repeat the procedure, so look what we get here. You get A11 multiplied by this one. You repeat this, you get A11 times A22 multiplied by, you know, A33 here, 0, ANN, 0 everywhere here, right? I mean, these are all zeros. And then A3N, and so on. In the end, if you repeat this n steps, you end up with A11 times A22 times ANN. So this is very important in the sense that you probably talked about the echelon method, and you know how to solve systems by using the echelon method. Well, you know, the matrix, I mean, the determinant of the matrix of that triangular, upper triangular matrix is the product of the elements of the main diagonal. Okay? Now, I don't know, we can go over a few problems from the textbook. So because, you know, I scanned the exercises in the textbook. Let me see if I can find them. Yeah, I found them. Here are, you know, exercises and problems from this portion. Choose one of these from 1 to 8. And then we can, you know, move down the list and maybe one from the other, or you can tell me whatever you want to see from, you know, the set of all these exercises.
Problem 5.
Which one?
Problem 5.
5, okay. I'm gonna move it from here. And let me look up, you know, the textbook if I have one. Yeah, actually, yeah, I have this. All right, so problem number 5 from section, so this is problem 5 from section 3.1. Okay, so what we have to do here is compute the determinant in these exercises from 1 to 8 using a cofactor expansion across the first row. Okay, in exercise, okay, so we need to use the first row. In the other exercises from 1 to 4, also compute the determinant by cofactor expansion down the second column. We can do it both, I mean, it doesn't matter. Okay, so here is the determinant in this exercise. 2, 3, negative 3, 4, 0, 3, 6, 1, 5. Okay, so this equals what? So we need to use the first row. So we're using a cofactor expansion across the first row. This is 2 times C, 1, 1, plus 3 times C, 1, 2, plus negative 3 times C, 1, 3. All right, so this equals, let's see. So this is 2 times negative 1. We know the definition of this cofactor. So you know that Cij, let me remind you that, is negative 1 to the I plus j times Aij, where Aij can be obtained, I mean the determinant of Aij, where Aij can be obtained by crossing out, is obtained by crossing out row I and column j. Okay, in our case, I'm going to cross out the first row and the first column, and what's left is here is 0, 3, 1, 5 plus 3 times negative 1 to the 1 plus 2, okay, multiplied by this determinant of the determinant of the matrix obtained by crossing out the first row and the second column. So 4, what's left is 4, 3, 6, 5. Okay, let me close this determinant. And then finally plus negative 3, so I have one more, right? Plus negative 3, multiplied by the determinant of the matrix obtained by crossing out the first row and the last column. 4, 0, 6, 1. Okay, so now everything is relatively easy. So we have negative 2 multiplied by negative, the first determinant, this one here, is negative 3 minus, okay, so here you have 3 times negative 1, so negative 3 multiplied by 20 minus 18 multiplied by 2. Okay, then negative 3 times 4. And look what I got. I got negative, actually 6 minus 6. These two terms cancel out. Minus 12. So what do you think? Well, you can do this in many, I don't know, software packages. I mean, you can use lots of software packages. Let me show you how to use MATLAB for this. So in this case, for example, let's say this matrix A is, it was 2, 3, these are the entries, negative 3. That was the first row. The second row is 4, 0, 3. And then the third row is 6, 1, 5. 6, 1, 5. This is our matrix, right? I hope I copied it correctly. Now, you can compute the determinant of A. It's a built-in function. And we obtain something different. Minus 24. I forgot something. Oh, yeah. Actually, I didn't forget anything. I just said something wrong here. 1 plus 1 here. Right? I mean, this is the cofactor. And that meaning this is plus. It's not negative 1. I forgot this. You didn't tell me either. It's 1 plus 1. So, in fact, these two don't cancel. Sorry about that. And we have negative 24, which is correct. Actually. Let me go there. So this is negative 24. Maybe I should erase this first. Just a little flow in this thing. This is correct, right? Plus 2 times negative 3 is negative 6 minus 12. Yeah. And as you can see, MATLAB gave us exactly the same thing. You can compute, determinant in MATLAB. You also know that if the determinant is non-zero, then the matrix is invertible. At least you know that for 2 by 2 determinants. If you remember from, I think it was in chapter 2. I don't teach, this class, but I looked up the textbook. So you know that the matrix is invertible or non-singular, even only if the determinant is non-zero. So in this case, for example, we can compute the inverse, A inverse. The inverse of this matrix A. We can say this is the inverse of A, and it exists in MATLAB. Well, of course, these are not, the numbers are in decimal representation. I can change that. So let's use, the rational format, and I'm going to redo this thing. This is the inverse of our matrix. Okay, you can compute inverses as well. All right, now I don't know. Let's choose something, one more from this section, and then we'll move on and talk about properties of determinant, which is section 3.2. We'll go back and forth between these two sections because there are so many. I mean, it's not like, you know, they are independent. Section 3.2 is based on 3.1. Anyways, choose anything from 9 to 14. So here we have to be smart about cofactor expansions and how to choose a column or row that involves the least amount of computation. Choose one of these from 9 to 14, whichever you want.
9.
Okay, 9. So I'm going to write it here. All right. So number 9, problem number 9 here, from the same section. Okay, so we have this determinant. Whose entries are 4, 0, 0, 5, 1, 7, 2, -5, 3, 0, 0, 0, 8, 3, 1, 7. Okay, it's a 4 by 4 determinant. And what do you think, what row or column should be chosen? I mean, to minimize the number of calculations or the amount of computation.
Row 3.
Very good. The third, this is perfect. I mean, this one. We choose this row because this is what we have. We have 3 multiplied by this cofactor. It's on the third row and first column, right? Then all the others are 0. I mean, plus 0 times C3, 2 plus 0 times C3, 3 plus 0 times C3, 4. But we don't even care about this thing because these are all 0. We multiply by 0 those numbers, right? So what we obtain is just 3. So let me rewrite this thing here. So this is 3 times -1. Don't forget about this one. -1 to this power 3 plus 1. And now we have to cross out row 3 and column 1. Okay, so in other words, cross out this. The row and column whose intersection is this number here, 3. Okay, so what's left is 0, 0, 5, 7, 2, -5, okay, 3, 1, 7. So this is out, this is out, this is out. Okay, let me just say that this one is not. Okay. All right. Well, now we have another problem, right? So this is 3 times this determinant. How should I compute this one? What row or column should I use for the cofactor expansion? I cannot read the chat. I mean, you'll have to speak up.
Row 1.
Okay, very good. That's, yeah, this is what you have to use. And so you get, this is 3. So I'm going to use row 1, right? This one, because it has the most zeros, which is natural, right? So I'm going to say, okay, so if I use row 1, this is 0 times C11. I don't care about C11 because it's multiplied by 0, plus 0 times C12. Again, easy peasy, it's out, plus, and now 5 times C, 1, 3. Okay, this is not 0, right? So this is 0. The other one, the second one is 0, but the last one is not 0. So I have 3 times 5 times -1 to the 1 plus 3. And now multiply by this determinant obtained by crossing out the first row and the last column. So I have here 7, 2, 3, 1. And fine, so we are done. Okay, so it's not that bad, right? Especially when we have zeros. I mean, 0 entries. Okay, this is 7 times 1 minus 6. 7 minus 6 is what? 1, right? So let me write it like this. 7 minus 6. So this is 15. This is what we get, okay? Now, of course, we can do exercises like this forever because, you know, there is no shortage of such exercises. But let's talk a little bit about the properties of determinants. That will enhance our ability to compute determinants, in fact. So I'm going to talk about section 3.2 a little bit, and we'll probably continue next time, either with Norma or myself. Let's talk about this. Properties of determinants. Determinants have very nice properties, very interesting properties, and somewhat unexpected, you know. Okay, so let's assume that we have a square matrix. So let's say let A be an n by n matrix, right? A square matrix. Then okay, so the first property, let's say A. If a multiple of one row, if a multiple of one row of A, of course, right, is added to another, added, I forgot this word, added to another row. I'm going to exemplify these things. To produce a matrix B, to produce, again, an n by n matrix, produce a matrix B of the same dimensions, then the determinants of these two matrices are equal. Then let me just the determinant of A and B are equal. I'm going to exemplify this, and actually we can convince ourselves about that. Another property is this one. Same thing with columns. So if a multiple of one, you can replace this word row by columns, and you get true statements as well. So I can say here column. Is that to another column here? You have exactly the same thing. So the statement stays true for columns. If two rows, this is the second property, two rows are interchanged, switched, of A are interchanged to produce B, another matrix B, right? To produce another matrix B of the same dimension. then the determinants of these two matrices are equal in magnitude but different in sign. So the determinant of B is negative, the determinant of A. And finally, another property which I can list here, if one row of A is multiplied by K to produce this matrix B, again an n by n matrix, then the determinant of B is K times the determinant of A. And I'm going to illustrate, all these three properties by one simple example. So I'm going to take a 2 by 2. So this is, matrix example. So let's take, this matrix, a very simple one. So we won't have to spend too much time with calculation and computations. So let's say negative 2, 3, 4, 7. And let's illustrate each of these properties. So, okay, property A. So let's, for example, multiply by Q. So I'm going to obtain this matrix B as in this way. Maybe I should write here. I can multiply the first row by Q. So let me just write it in a more understandable way. So let's say the new row RQ is just RQ times R1 plus RQ. Okay, so I obtain this matrix B as being the first row stays the same, but the second row is changed in this way, twice the first row plus the second row in A. Okay, so I mean twice the second, the first row means negative 4 plus 4, this is 0, right? And then 6 plus 7, 13. So this is how I obtain B. Okay, so B is given in this way. Let's compute the determinants of A and B and see whether they are equal or not. They should be, according to this first property. So what's the determinant of A? Well, it's minus 14, right? Plus 12, minus 12. So it's minus 2 times 7, minus 4 times 3. Okay, so negative 14 minus 12 is negative 26. Okay, now let's look at the determinant of B. Let's compute the determinant of B. This is negative 2 times 13 minus 0 times 3. Again, negative 26. You don't change the determinant by doing that, right? Now, let's exemplify part B in this, very particular situation. We obtain this matrix B by interchanging the rows of A. So I have here 4, 7, negative 2, 3. Okay, which is what? Is 12. 4 times 3 is 12. Minus 14 plus 14, so this is 26. Well, this is just, well, the determinant, right, of this. Maybe I shouldn't say it like that. So this is B. And the determinant of B is 12 plus 14 is 26, which is exactly negative determinant of A. It's exactly what we have here, right? And now let's multiply one of the rows for part C, multiply one of the rows of A. So let's say we multiply the second row by 3, okay? And we produce this matrix B. So this is negative 2, 3. I multiply the second row of A by 3. So this is 12 and 21. Well, this is what? Is negative 2 times 21 is minus 42, minus 12 times 3. Okay, so this is minus 42, minus 36. This equals minus 78, which, by the way, is just 3 times negative 26. And so this is 3 times the determinant of A. And that checks out, the third property. We'll continue with these properties next time if Norma doesn't show up. Otherwise, Norma will take over. And if you have any questions or anything before we leave.
Yes.
Yeah. Questions?
Yeah, it's about the class so far. Our instructor last class said she would post homework right after last class, but she never did. So I was just wondering.
You have to ask her. She didn't tell me anything about the homework or anything.
Oh, okay.
Assignment. I mean, I have no idea about that. It was a last minute, I don't know, let's say takeover. Okay. And she didn't tell me anything about the assignments or. So I got the book immediately. I looked up the book and okay, yeah, I know determinants. I can, So you have to ask Dr. Elias for this.
Okay.
Right. I mean, I don't know. I have no idea about the assignments or the due dates or what you have to do in terms of this.
Okay.
All right.
Thanks.
Okay. Other questions or comments or complaints? Anything? All right then. So have a nice evening. The attendance is taken automatically. Zoom records, the attendance. And I hope to see you again. Okay. I hope Norma will get better and be back, but I like the class.
All right. Thank you. Have a nice day.
You too.
Thank you.
Bye-bye.
Bye-bye.